Okay, so now let's state and prove the Bloch theorem. So the FC be analytic. In the unit disk. D. So I just use D for the unit disk and satisfy the condition that f prime 0 equals to 1. Okay. So then there exists a subregion remember subregion is a subset, not empty subset, that is open and connected. That is mapped univalently so remember that univalently is it means the injective for holomorphic function. Usually by adding onto a disk of radius b, where this constant b is independent of the function f. Okay. So that is this b is an absolute constant. Okay. Yeah, so here's the proof. All right, so for the proof, we temporarily assume that this f is so we temporarily assume that so this Fz is analytic in the closed disk, debug. So assume that. So now we set this M1 to be the maximum over set 1 minus modulus of v squared times f prime v. So yeah, over where v is taken in the closure. Yeah. So basically, we take the maximum over this function over the closed disk. So then, because this f prime 0 is equal to 1, so yeah, so basically, so we have this M1 is bigger equal to 1, right? Yeah, so when you plug in 0 here, right? So you get here as f prime 0, and then here we get 1. Okay, so this, yeah, so this means that this maximum must be bigger than equal to 1. Okay. All right, so now let alpha be a point such that this 1 minus modulus of alpha squared times this f prime alpha is equal to m1. Yeah. So remember that this m1 is being a maximum over a of a continuous function over a complex set, so it must be achieved. Okay, so within the set. So therefore, we know that it is equal, there is some point. So alpha is actually in the disk closure, right? Yeah. So yeah. So click then. Clearly, we have this modulus of alpha is less than 1, right? Because the modulus of alpha can be equal to 1, otherwise this m will be equal to 0, right? So which is cannot, yeah, so must be less than 1. So so now we define this another function f of zeta equal to small f of v, where this z is equal to alpha minus zeta over 1 minus modulus of alpha zeta. Okay. Yeah, so we define the this big F to be F of Z, where in terms of zeta. Okay. Yeah. So therefore we have let's see then this 1 minus modulus of v squared is equal to so so here we do a little bit of computation here. So so we calculate the modulus of z squared. Okay, so the calculation is a little bit tedious, so I will just write out the result. So the calculation would be 1 minus modulus of alpha squared times 1 minus modulus of beta squared over modulus of 1 minus modulus of, sorry, what I mean is the complex conjugate of alpha times the complex conjugate of zeta squared. Okay, so yeah, so that's that. And then, okay, so now we compute this, remember that this z can be viewed as a variable of zeta, so now we compute the derivative. So now we have that, therefore the dz over d zeta is yeah, so we apply the quotient rule here, and then we add the modulus. So what we get is, we will get the bottom as, yeah, so we will get that. The bottom is 1 over modulus of alpha, zeta square, and the top is 1 minus modulus of alpha squared. Okay. Alright, so for this one, we know that oops, sorry. So 1 minus modulus of b squared. Yeah. So yeah. So you see that this quantity, right? So this quantity is actually yeah, so if you take a look at this one, right? So this one is actually this whole thing divided by this 1 minus zeta squared, right? So I can write it as, and then zeta can yeah, zeta cannot be equal to 1, I want to say. So yeah, so basically you know, this is like a yeah, this is like a Mobius transformation, and then this zeta can only takes value from 0 to 1. Okay. All right. So yeah. So this tells you that this 1 minus zeta cannot be equal to 0. Okay. And then I think you can see, and the bottom is also not equal to 0 because yeah, I think this is by some like like E equality. Okay, yeah. So let's see. So why it cannot be equal to 0? Okay. So we will figure that later. Okay. All right. So right now what we have is we have so this is equal to 1 minus modulus of v square over 1 minus modulus of zeta square. Okay, so we have that, and then we want to have some okay, so therefore what I want to say is that 1 minus modulus of zeta square times modulus of f prime of zeta, which is so this guy is equal to 1 minus Yeah, so when you are taking this f with f prime theta, right? So what you're really doing is that you are using the complex chain rule, right? So yeah, so basically you are using the chain rule. Yeah, so basically what you're doing is equal to, let's say 1 minus theta squared over the modulus of, yeah, so I'm skipping one step. So it is like this f prime z times, it's really like dz d zeta, right? And then the modulus over the whole thing. And remember that the modulus of the product is equal to the product of the modulus separately. So I get that. And then, so this one is equal to, yeah, so remember that this guy is just this guy, right? And then we have 1 zeta squared multiplied at front. So therefore we get 1 minus modulus of z squared times modulus of f prime z. Okay, so okay, so sorry, right here. Okay, so the thing is that this let me see. Yeah, so this guy is exactly this one, right? So this one, I know that it's less than equal to m1, right? So therefore we have this whole thing is less than equal to m1. And then, so because this zeta is any zeta that, yeah, maybe I should add on, yeah. All right, yeah, for all zeta we have that. Okay, so now while we are choosing this alpha, so I think one of the reason is that, okay, so when this so okay, so because this zeta equal to 0, so when zeta equal to 0, you see that this is 0 minus, it is just alpha, right? Corresponds to this z is equal to alpha, right? So so we obtain this f prime 0, sorry, the modulus of f prime 0. So it's actually bounded by this m1. Oh, did I miss something? Hold on. yeah, so make a mistake here. So, okay, so I should be using, yeah, so I'm using this relation, okay. So basically you know that, yeah, so basically, so when zeta equals to 0, you will have, so you just look at this one and this one, okay. So when zeta equals to 0, you will have this as 0, this whole thing as 1, right? And then, so the left-hand side of this equation will be just modulus of f prime 0. And then when you plug in zeta equals to 0 here, you will get this z to be alpha, right? So, and then this is f prime of alpha. Okay, so we have, so we obtain the modulus of f prime at 0 is equal to 1 minus modulus of alpha squared times f prime, modulus of f prime alpha. And then, which is attain this m1, which is equal to this m1. Okay. So, all right. So now what we do is that, okay, so I'll erase the board here. So therefore, the function g of theta, which is defined as f of theta minus f 0 over f prime 0. So this function satisfies okay, let's see. G of 0 equal to 0. Okay. So basically if you plug in 0 here, the top one will give you, the numerator will give you 0. Okay. And also G prime at 0 is equal to 1. Right. So when you take the derivative, it will give you the f prime 0, right? Okay. And then, so the modulus of G prime zeta basically it's the modulus of this f prime zeta over x prime 0, right? Yeah, so which is the modulus of f prime zeta over f prime 0. So remember that this modulus of f prime 0 is equal to this 1 minus alpha times f prime alpha. Okay, I think maybe I need a little bit of manipulation. So from here we know that this so here, so basically what we can say is that we can say this f prime zeta is less than equal to this m1 over 1 minus zeta squared, right? So yeah, so then this f modulus of f prime 0 is exactly equal to m1, right? So we can say that this is less than equal to yeah, so 1 over 1 minus zeta squared. Yeah, because the top is less than equal to m1 over 1 minus modulus zeta squared, and the bottom one is equal to m1. Yeah, so just divide it out. Okay. All right. So for all, yeah. Yeah. Okay. Okay, so now what we want is that we want to find a upper bound. So of this modulus for for this zeta in this closed disk, and then for any radius between 0 and 1. Okay. All right. So the thing is that okay. So what we do is that now we fix a point. Okay. So zeta naught is equal to this r into the I theta. So and then lies on the boundary of this closed disk. Sorry, it's not, but yeah, you know it's the boundary, right? So then, so we have that this g of this zeta naught, so which is taken over the complex integral from 0 to zeta naught d zeta, right? So where you can view this as integrate over any, let's say, C1 path from 0 to this data over all this G prime data, d data. Okay. So and then so integrating along radius of the unit disk we obtain okay, so this modulus of this d zeta naught is less than equal to this the integral over from 0 to this r. So just here, yeah, g prime of r e to the I theta dr, right? So just imagine that you are just taking over this yeah, radius curve from this 0 to r. Okay. And then so this is less than equal to integral from 0 to r dr over. So here we use the previous result, right? So we use the result that is g prime theta is less than equal to 1 over 1 minus modulo of theta squared. So what we're doing is that because we know that here the modulo of theta is just r, right? So here is less than equal to 1 minus modulo of theta, which is just r squared dr, right? So now and then so this integral is like a integration, and then it gives you 1/2 natural log of 1 plus r over 1 minus r. Okay, so actually you get a exact upper bound for this zeta, right? So what's the time now? Okay, I want to say that, okay, so, so this data node is taken in, okay. Oh, shoot. I think maybe I made a mistake. Okay. So, yeah, so actually, let's see. Okay, so let's maybe consider changing these to this little r prime. Okay. Where this r prime is less than or equal to this r. Okay. So yeah, because so basically this one still holds, right? So if you have this r prime, so you just replace, this is all positive, right? So this positive, and then you integrate from 0 to r prime, should be less than equal to integral from 0 to r, right? Because this r is bigger than this r, right? Okay. So we have alright, so therefore what we have is, so therefore we have shown that for okay, so I'll stop here and then we shall continue next time. Okay, so yeah.